To begin with, as usual, there are always a couple of announcements. The first is that the conference dinner's tonight at 7:30 at Rice College. There are maps around various places, and it shouldn't be hard to find. And most likely a bunch of us will walk over from here. So,
when do we start?
we're supposed to be there at 7:15, so probably 7 o'clock. That's item number one. Item number two is the group photograph is happening today at 12:30. So be here and we'll find a place. Our first speaker this morning is Martin Loebl from Charles University, playing the Wick game.
Hello. So I want to speak about a subject which many of you know better than me. But I want to look at it from combinatorics point of view. Is probably this great machinery. It's in fact combinatorial machinery of Wick theorem. It seems to be it's a beautiful basic principle in counting, in expansions of integrals. Slightly funny thing is that even though it has strong combinatorial flavor, probably it was actively looked at by combinatorialists relatively late, but now it's quite active subject. There is a great survey of Di Francesco, and there is a book of Zvonkin and Lado. Part of it is devoted to applications of Wick theorem for matrix integrals, and I learned a lot about it from people from Bordeaux. So just to start, so what I will do usually, what I want to do. Usually this metric, I will speak about matrix integrals, and they are usually applied to functions, to polynomials of traces. And typically you get some enumeration related to maps. So maps, that's another thing. So you here often, so for terminology, often it's not, during the lectures, it's not distinguished whether one speaks about planar graph and planar maps, because usually it's clear from the context, but here it's kind of more important. So enumeration of planar maps or maps embeddable to orientable surface is a classical subject both in physics and in combinatorics, but it seems to be much more complicated for embeddable graphs. And there was a beautiful lecture of Mark Noy about some of the difficulties. So I will speak about embeddable graphs, and somehow our motivation was to try to apply the machinery perhaps to different functions to get not to polynomials of traces, and to get to express the number, let's say, of planar graphs, of graphs embeddable to the plane as a matrix integral, or with hope that it can be carried to other surfaces, as in the case of maps. So that's why, so the basic, so for maps, it's beautiful, elegant, and it is it's based on interpretation of matrix elements in certain way, and well, for embeddable graphs, we need to interpret it in a different way. Somehow you will see that somehow our interpretation is dual in a sense to the standard interpretation of matrix elements for this Wick theorem application. And so let me go briefly through the basics. So it is, well, it's just the basic trick, very nice trick. When one counts Gaussian integral of polynomials is to calculate the source integral. It's easy, and then the Gaussian of a polynomial is just derivative. Oh no, it doesn't point. Here is. I am spoiled with these machines that you can. So so for polynomials, so once you have this, you have all polynomials because you get them as derivatives. So it's one. So it's standard trick, and it's exactly the same for matrix integral. So you again you get you make the source integral, and then for the integral of any monomial or polynomial in the matrix elements can be expressed using it. And in this very elementary way, one gets the Wick theorem for this matrix integral case, and it is it's so of a monomial product of entries of matrix is some overall pairings of elements of this index set, and well, the only those pairs contribute if well, if I is L and J is K, and then they contribute 1 over n.
So let me just understand. When you pair two m's, you have to pair both indices together, or can
You play,
get one
yeah,
index?
yeah. I will maybe this will be an example. Is it
No, the it'll only come, I guess, when you
0 if it's different and 1 if it's.
When the edge is different.
So yes.
Chronological delta with respect to edges.
Yes. So it's this is 0 if I is different than L and J, or J is different than K. Okay.
So I guess the question I'm asking, imagine you have 3 m's. What are the allowed pairings? Or 4
I don't. Oh, you have. So these are indices of the matrix. So they are these elements of I are always pairs.
And so you have to do the pairing in pairs.
Yes. You pair the pairs.
Okay.
You pair the pairs. It's
Oh, and these are ordered pairs because they
yes.
Hermitian rather than symmetric.
Yes. It's matrix. You have yeah. So this is the game. So that is it's easy, elementary, but and you can look at it also from abstract point of view. That discrete point of combinatorial point of view. That you have a polynomial and a game applied to it. Is this brackets applied to it? Pops out this thing, right? And well, a natural question is, what is it good for? Whether you can, in an abstract sense, if are there some interesting polynomials for which this which gets out has some interesting meaning, and then of course, if that is the case, whether one can evaluate, then one can go back and whether some analysis of that function f and its integral is possible. So the classic example is, so how to get something meaningful by interpretation, by doing combinatorics, by interpretation of the matrix elements, so on. And classic example is enumeration of maps, and then it's the matrix element is interpreted as kind of double half edge, all right? And that seems to be the best interpretation. And I don't know who came with it. I don't know whether Di Francesco or it seems to or earlier. Much.
Tahoe.
Oh, okay. So okay.
Edmonds.
Okay. Well, but
Many times.
Edmonds. Well, but whether Edmonds, I don't know whether Edmonds knew this matrix integral. I thought, well, there is, of course, there is this fact that these matrix integrals count maps. Of course, it was real. People knew it much before. But I'm speaking about this this graphic interpretation.
Yeah.
That is beautiful and kind of.
I think the first place I know about is in Tahoe.
Oh, very nice. Thank you.
Because physicists had for a long time been considering these kinds of Feynman diagrams with either scalar or vector fields. And so this is the natural generalization to matrix fields.
Yes. So it's very nice, straightforward. So then you interpret this bracket of product Mijkl as 1 over L. This let's say this edge, and it's 1 over n times this in case Li is equal to I and k is equal to j. So in fact, the good thing is one should really say that the index is no more on vertices, it's on the edges. The edge has weight I equal to L, and yeah. So this is so for our purposes to enumerate embeddable graphs, we need to change this. That will be different, the basic interpretation. That's why I somehow go through it. And then, so yeah, how do you get maps? Let me just quickly indicate it. If your function is let's say trace of m to the 4th, then which is just this, then what is it? So each this term you interpret as this 4 kind of 4 half double edges glued together. So again, this index on the vertex I1 means that these 2 edges get I1, I2 means that this 2 gets I2 in any non-zero contribution. This I4, this I3, and so that is interpretation of each term to which we apply the bracket. And then, well, what is the bracket? It's sum overall these indices, and then sum overall pairings of this thing. So, well, what does it mean, the pairing here? You pair these pairs, these 4 pairs. These are all the possibilities. And in order to get, so these somehow are the Feynman diagrams. They are the pictures for the game. And if you want, so how much do they contribute? Well, as I said, these indices somehow, they get, in a non-zero contribution, they are inherited 2 edges. So you want that whenever you walk around in a curve, it's monocolored. It has 1 index only. So, well, this, so what it is, so the contribution is sum over all these pictures of n, maybe, no, it's over n to minus EF, because it's 1 over n, and EF is just the number of these pairings, right? And PF is the number of directed cycles which are there. So soon you will see what they are. So this picture which we saw, it's a map with 1 vertex. You walk around. Well, they are faces. They are really the what they are components of the boundary. If you look.
How many there are in the third picture?
In this picture is 1, I think. Let me see. Yeah.
Yeah.
Is 1, I think.
How did this come from the width?
It is because you need so all these pictures are just the sparings, but well, the pictures with the indices, right? Each picture each picture comes with a lot of indices. Not all indices contribute non-zero. So which choices contribute non-zero? Let's have a look at it. Well, those where each edge is monochromatic, right? So this index, let's say I2, it means that this edge should have color I2, and the whole edge, not only this end vertices. This edge also I2. So in other words, if I turn around, I must have the same color. So all these components of the boundary must be monocolored. So it is this n to pf. Because n is the number of colors. Its matrix is n by n. Sorry, that was the question. Sorry. Long explanation, but I got there. Okay, so what are those pictures? Well, all of you know they are maps. So they are maps, but actually it suggests to look at it as fat graph. It's just vertices are islands and edges are kind of bridges, and these cycles are just components of the boundary of this thing, and there are faces, and there is Euler formula, which that's the lucky thing, because then in the limit one recovers the genus zero contribution.
So just say again about the combinatorics of this. Having a graph, an ordinary graph, together with a fixed cyclic ordering of the incident edges of each vertex is equivalent both to giving an embedding of it in an orientable surface, and is also equivalent to a unique way of making a ribbon graph.
Yes. So yes, exactly. So the ribbon graph, there you see immediately this permutation of edges at each vertex, right? And that's a deep classic theorem of Edmonds that is exactly map.
Oh, I see. The cyclic ordering is because you can follow the two sides of the ribbon.
Yeah.
So therefore, from now on, we don't have to talk about ribbon graphs. We can talk about ordinary graphs with this cyclic order.
Or maps or ribbon graphs or fat graphs. But all this is matter of fashion. I think that in maybe in maths in this mathematics community, discrete maths, or in some parts of topology, which I know, the notion of fat graph seems to be popular. So
fat graph is the same as ribbon graph?
I think so.
Okay.
Except ribbon graph you can do unoriented because you can take it out
and
and
twist.
sunwards.
I see.
Okay, so
I see, but here that never happens?
you don't twist. It's just the bridge is normal.
Symmetric matrix to twist.
Oh, I see. If you had done symmetric rather than Hermitian matrices, then these things could twist.
I don't know.
I'm not sure whether it's right.
I don't know. Okay.
Because then there would not be directed edges.
But you want both twisted and non-twisted, so you just...
You don't have directed edges. You have just edges.
No, but here, go back. I mean, here you had coming out of each vertex direct to a pair of directed edges.
Yeah. So, but that is the
One is going one way and the other
Yeah.
is going the other way.
Yeah.
Therefore you can't distinguish anything.
yeah. So it's
But I thought it was that for Hermitian you only have untwisted, and for complex you have twisted and untwisted. Complex, double.
oriented edges.
Yeah, because you can...
No, you're yes.
And it's real symmetric.
anyway. Let's
But if
move
you want
on.
with letters, you have just
So if you for more complex you have let's say if you have a polynomial in traces, then you have then the interpretation is sum over all pointed fat graphs with 4 vertices of degree 3 and 3 vertices of degree 2. So let me explain it. So this is 4 vertices of degree 3 and 3 vertices of degree 2. They are this. Where is the third one? Now I don't see it. I forgot it. There is. I'm sorry. It's there is one more.
You have to choose some edge and
Yeah, yeah. And yeah, okay. Good. And why pointed? Well, pointed it is because it's trace, so it's start.
what do you mean by pointed?
It's you specify an edge at an edge incidence to each vertex. Okay. So if let's say I want to interpret this. So if I want to change the game, all right. So it's and also I'm doing combinatorics. So I just move from the first step is to move from matrices to directed graphs, and that's easy. That's straightforward because each matrix is a directed graph, really. So what you do, so each matrix element ij you interpret as an edge going from I to j with weight mij. And then, so it's complete directed graph. So between each pair of vertices, there are 2 edges. And now this function, this thing, really, what is it? It's this. It can be written as sum overall. So what is this? Well, this is the trace, right? It is sum over pointed closed walks, which have the beginning. They are directed, and they are. So these have length 4, and these have length 3. So this trace, this function, can be interpreted as sum overall all things which are called Q. Q are here 7 pointed directed closed walks, 4 of length 3 and 3 of length 2, and this Q, so it's as a set of edges, is given together with its decomposition into Q1 up to Q7.
So can you explain again what you're doing here? You're giving a new graphical representation where in the old one we had a pair of nearby points representing an MIJ, right, with one half edge going in and one half edge going out.
I did not get to it yet. I did not.
No, but I'm just trying to understand what you're doing here. You had a previous graphical representation where an MIJ was 2 nearby points with a half edge going in and a half edge going out.
Yes.
Okay.
And this is dual, yes.
You're taking that and also drawing an edge from I to j
yes.
with an MIJ written on it.
Yes. So that is
So
actually.
you're explicitly showing by directed edges with MIJ written on them where the
Yes.
Okay.
And that is actually, you see that it's kind of dual for the, well, that I will get to it perhaps later.
Can you explain again where the pointed comes from?
The traces beginning is, it has,
It's the same modular
Yeah.
cyclic permutation, so it doesn't, why
Yes,
does it make a
yes.
point?
So it doesn't have the
It doesn't have a beginning.
Can you show us a picture? I mean, this is a new kind of picture relative to your old kind of picture.
yes.
Can you show your new kind of picture for this?
Oh, well, let's, that I think, so, yeah, so, so let me see, so here is this, this is the interpretation of this is how you look to matrix elements for this matrix integral and for the standard interpretation. And over here, so far, I did not I did not interpret the matrix, the Wick theorem contribution. I did only, I said, and that I said how to look to matrix in a different way. I don't, and it is that to each matrix element I associate H like this. And in fact, it will turn out that that will be the way to look at the Wick theorem, Wick contribution. Right? So that's so what I wanted to say is that when maybe I have it in this. Yes. So here it's so the walk. So it's some overall walks and or closed walks and walk in the classical interpretation for Wick theorem is interpreted as half edge, double half edges going from one vertex. All right. So in this sense, it's dual. This view to the walk and this. The pointing, it's just that trace is some of the diagonal, right? So it is.
This is technically symmetric.
Yes. But it is when you have it lives on the directed graph with names on vertices. So it is the contribution of AI in this power is of the i's entry of the diagonal are the walks which are rooted in vertex I somehow. Or maybe, well, it's triviality. I'm sure we mean the same thing.
Maybe you also mean that if every time that you have trace of m to the k, you put a 1 over k in front, then you have the...
And then you don't, but... Yeah, but that's what you do when you count it. So you always have to take care of this rooted. That's why in these formulas, these factors appear, this linear factor. So, okay. So here is the main goal was that whether one can express enumeration of embeddable graphs as matrix integral. And the trick is that one needs to avoid this. Right? So why the classical interpretation counts maps? Where this embed this, what is a map or fed graph is something where at each vertex, edges incidents at each vertex are ordered. There is a cyclic ordering. Where it appears? Well, it appears in the definition of trace, right? Because there, in the trace, you start somewhere and you walk, and that really the walk, interpreted dually, are edges incident with a vertex, and that gives you the cyclic ordering, right? It's in fact pointed cyclic ordering. And so one needs to relax this. If one wants to count something else, one needs to relax it, and there is an obvious relaxation for pointed closed walks. And that leads to the notion of Eulerian subset of edges. So if you have a digraph, but we really have complete digraph, but it's for any digraph, we call a subset Eulerian. If it's in degree, it's if for each vertex, the in degree is equal to out degree. In degree are all the edges going into it, out degree all the edges going out. And it was in fact quite a surprise for me that this, in a sense, works. That a relaxation of this sort works for counting embeddable graphs. So let me say it concretely. Let's consider this function. It's a ice-type partition function. So it's some overall a Eulerian subsets of ED. Of here is just product of matrix elements corresponding to A. Then there is a contribution of the components of A. It is it's this really is a notation which even would be confusing for combinatorials. Component is components just connected in if you forget orientations, but I take all the edges, not vertices of that. So usually by component you always look to the vertices of the component, but I look to the edges here. So the C over 2 is the number of these directed edges which are there.
Can you draw one on the blackboard? I don't think I understand.
Yeah, I don't understand the product of matrix elements.
So this is so E is a directed edge. It's so each E is form ij. So it is this that you interpret matrix as directed graph. In this sense, not in the in this dual.
I'm sorry, the I and J, the indices, I mean, I don't understand what, oh, I see, the vertex set of this graph is the index set of the matrices.
Yes, yes,
Ah, okay.
yes. And for the, well, for, so this is one component,
Okay.
this is the other component, and well, this is 3. Here the size of C is 3 and here 1.
But those are not Eulerian.
Yeah, but that was not the question.
Martin, what do you mean by an embeddable graph?
It's that they have a graph. So yeah, so planar graphs are those which have planar drawing. Toroidal graphs are those which that's I mean embeddable. I mean I should say embeddable on surface of genus G. Orientable surface. Yeah. So that's.
The point is that each of those will give rise to many maps when they are embedded.
Exactly, that is the whole point. It's hard, it seems to be, up to the present knowledge, it seems to be much harder to count embeddable graphs than maps, than embedded graphs. Maybe in the end it will turn out other way, but now it's hard to, there is Mark Noy and Omer Jimenez can count planar graphs embeddable on the plane, but yet nobody can do toroidal graphs, right? So there are beautiful open questions actually. There is, for instance, there is a characterization of all possible planar embeddings of a graph. There is this width switching theorem. Nothing like that exists for toroidal graphs. It seems to be given a graph, given toroidal graphs, it's nobody knows how to characterize its embedding to the torus. It's even yeah.
You already have embeddable graph. You know
Yeah.
that it is embeddable
Yes.
torus, and you know.
You want to
you know
characterize,
which-
yeah, how to embed it. So that one can do for the plane. It's a beautiful, very old theorem
You
of
can know that
Whitney.
it is embeddable without knowing how to embed it. You know.
Whatever. Let's.
Is the point, given
Let
one
me-
embedding, can you construct all the other embeddings?
So this is the theorem. It says that there is one byproduct of this other interpretation is that so at this without making limits everything is finite. So there is no problem with convergence, and so then when it goes to the in the limit, which we did not do, then I am sure it will appear, but not yet, because this is just a polynomial. It's because it's finite. This G is finite.
Can you start from the beginning and
Yes.
tell us
Yes.
Can you maybe just read it out? What's the
This. Oh, sorry.
Just what are the letters?
This slide.
E, Z, and there's an
What? Sorry. Where are you?
Is there an R?
GM.
I type.
Is this, the second entry is a capital N R.
So they are those. Yeah. Sorry. It's.
Frame Z.
This is Z and this is Z. Yeah. Oh, sorry. No, yeah, it is the same Z. Yeah. But no, sorry. So it is Z. That's Z. That's it.
Only two variables, Z and Y.
Z and Y are variables. N is the size of the matrix.
Is it true that you can have multiple edges between I and J, even directed?
No, you have only this.
At most one.
At most one going from I to J, at most one going from J to I.
But not if you just expand the exponential. In that case, you would have had multiple edges. So
Well, we don't really, we consider only finite, so we really don't take the complete expansion of the exponential. We cut it from, but even then, I am not sure whether what you are saying is right with these
So these are
double
simple-
edges. But we can discuss it.
So these are simple Eulerian digraphs, no more than one edge in a given
In the same direction between two
and,
variables.
and
Yeah.
no loops.
No loops. No loops. So, okay. So, what these strange things mean is that, well, first of all, this is clearer. It means that we look only to this is to the contributions of we look to the contributions of we compare indices of terms in the where the total degree of the variables is at most n over 2. Okay, so it is it's technical. This is kind of a polynomial. This in fact is a series, so somehow one needs to say where to cut it, right? We say that this this inequality is true for the coefficients up to the total degree n over 2.
So how should we read this? Should also start from the beginning with P and R is unlabeled connected.
Yeah, sorry. Yes, you're right. So
And there's suppose an E1 or something.
they are, yeah.
Something.
All right. So what we are interested in are the PNR, which is number of labeled connected simple graphs on n vertices which have planar embedding with R faces. All right. So it is that is this PNR. All right. Now E1 is error term and E2 is error term, which with n go like it's big O of 1 over n. And that is interesting, these error terms, they contain contributions of higher genus. All right, so potentially we hope that, so this is a formula for planar graphs embeddable to the plane. But that is the beauty of this application of Wick theorem, that it gives the contribution of other, of all the genuses. Right, when you take first error term, second, and so on, that gives the whole generating function of all genuses. So it's easier for this maps for this classical interpretation. But so for us, this because there the error terms have only contributions of maps of higher genus. Here it's spoiled a little bit because of this other interpretation, all right? And but still it's spoiled in kind of simple way. We strongly believe that this one can get formulas for arbitrary genus. Okay. But yeah, so that's it. So here we cannot prove this lower bound. It's with slightly worse than n over 2. So this S goes to infinity slower than n.
So it says that the first line is the first few coefficients somehow.
Yes,
It's the same thing as
it's at most this and
the middle.
yes.
Or is at most?
Yes.
At most means coefficient-wise?
Coefficient-wise, yes, yes.
And so if you only go up to
Well, up to
first row and here the first and after.
yes, 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 exactly. So in the well, if we don't do limit, but in the it's prepared for making the limit when n goes to the infinity. So, but before that, before going to the limit,
So
yes, sorry.
You mean that you think that this is also true if you go to the next term, the E1 term, and select the genus 1?
Yeah, yeah.
Yeah.
That I strongly believe that it will be that something like that will be possible. But before doing that, and we are already somehow the formulas for doing it. But well, before doing it, the meaningful. Is it meaningful? In other words, all right. So this is somehow let's say we can express this number of planar graphs embedded to the plane as an integral. But is there a chance to count the integral? For instance, it would really, that I think should, I mean, at least for us, comes first, this way before doing further this analysis of these genus contributions. So we would really love to get again something like this result of Jimenez and Noy to calculate. Well, we would love to calculate, right? And for calculation, one needs to make matrix integral of this type of function, and it's nice function. It's let me 1 minute. It's an ice type partition function. So it appeared in knot theory. It appeared in a lot of things. Where there the ice is really on the square grid. Here is ice on this complete graph, right? So it's somehow maybe a general question, because as far as I know, which is not, unfortunately, not too much, this analysis, asymptotic analysis, is done only for matrix integrals of functions of traces, of polynomials of traces. And this is a different function. This is let's say ice partition function or Tat polynomial, right? Or Ising partition function or things like that. Is there a hope to do an asymptotic analysis or some estimations for this matrix integral? And that's one thing. So sorry.
I just missed something. What is D? It's the complete graph.
Yes, it's complete graph with it's complete directed graph. So between each pair of vertices. So
May I say also, you are using ice type as a name, also vertices have not degree 4 in general.
no, well, but you can look at the ice type as some overall Eulerian orientations of a graph, right? If you for a typically graph is square grid, and you take some overall possible Eulerian orientations of that, of something, right?
There is however a gap in difficulty between
Yes.
degree 4 and arbitrary degree.
Yes, but yes, of course, but this is just it's well, that's what you get. That's so we want asymptotic analysis and. Well, anyway, this is what we get. We don't actually originally we got much more terribly looking function, but this is somehow what for me it was a surprise that well, the question is we'll deal with it purely combinatorial graph theory, and you get something which has meaning in statistical physics. So maybe there is, well, it's, maybe it's, there may be something hidden behind. Yeah, I wanted to indicate how to prove this, but I have no time. So only maybe there is 1 minute. So there is, unfortunately. So there is another, we have another formula for counting directed cycle double covers. There is a beautiful, one of the main open problems in discrete maths is called cycle double cover problem. It is it true that any graph without a bridge is this is a bridge, okay? It's an edge which if you delete it, it disconnects. So is it true that any graph without a bridge has a collection of cycles of length at least 3, so that each edge is in exactly 2 of them? Each edge is in exactly 2 of them, okay? So in each edge you have your strange cycles. Now we are speaking about abstract graph. Each edge is in 2 cycles, right? It was discovered it's very old. It was discovered by Sekeres and Seymour and many others. It seems to be very hard. No, very little is known about it. It's the directed cycle double cover conjecture is that you can prescribe moreover orientations to these edges, so that on each edge it's the orientations go oppositely, okay? And so there is another way, so we can count the number of pairs graph and its directed cycle double cover graph at most n vertices, also as a matrix integral. And here it's a different function, but also quite nice. It's this Ihara-Zellberg type function. It's basically infinite product. It's almost a determinant. It's not a determinant because some rotation is not correct, but it is. It's an interesting function somehow. It's not nothing crazy. So it's again the same question. Yeah, yeah, that's it. Thank you for your attention.
Perhaps we have time for 1 or 2 questions. Are there any more?
So no. Okay. So you're telling that with matrix type integrals you can count the graphs which allows for an oriented double circuit.
Which have it, so I can count pairs.
You also count them with the number of which they have.
Yeah, well, I count pairs, graph, and its directed cycle double cover.
So the idea is that if this number is not growing too much,
Yeah,
with the number of graphs,
exactly.
you can maybe disprove it with saying this function grows
Exactly.
less than the number of graphs.
Yes. So there is a classical approach of Tat to prove four color theorem, and that was actually the initial point of Tat, why he began to count maps. All right, and so well one can hope to perhaps to do something similar here for this directed cycle double cover. So that is motivation. When split says that, once when it reminded me one problem which I will ask this physics audience. It's another problem which I got to know, apparently old, so big price, which somehow is very easy to, which I got to know recently, which it's very simple. It's so for physics audience, one can formulate it in this way. I take a triangulation of any orientable surface, like in plane it's known, but take -1 weights on each edge, and take Ising partition function, so this or spin glass Ising partition function, and you want to prove that there is exponential number of ground states. So there is, for all regular triangular lattices, it is of course known by transfer matrix method, right? But is it true just for any triangulation of a surface? So this is apparently a long-standing open problem. So,
so the statement would be that there exists a constant. I mean, there exists a constant A and a constant B greater than 1. Such that for every n vertex triangulation, you have that.
Of any surface, yes.
But you have,
yes.
But that's proven for planar, you say?
It's proven very hardly. It's proven by big guys, Seymour and Maria Chudnovska, and from Princeton, and it's proven only using four color theory. And so big canon and very good people. And in fact, so the original problem is formulated in a different way, but to use this for the reformulation which I use the validity of directed cycle double cover conjecture. So, but that's somehow, okay, thank you for your attention.